Have you ever wondered what it would be like to actually outrun the sound you're making? We're all used to measuring speed in miles or kilometers per hour. But for fighter jets, for spacecraft, that's like using a ruler to measure a skyscraper. There's a totally different and, frankly, a much cooler way to talk about speed when you're on the edge of what's possible. So let's get into it. So yeah, why is that? You see it in movies all the time, right? The pilot yells, "We're going Mach 2," instead of, just saying a speed we'd all understand. Well, I can tell you, it's not just for the drama. There's a really important scientific reason for it, and it kind of changes everything you think you know about going fast. And that brings us to our first major point. We needed a better way to measure speed. Because when you get up to these incredible velocities, it's not just about how fast you're going, it's about how the world around you is reacting. The air itself becomes this massive part of the whole equation. See, when you're driving your car down the highway, the air is just, a slight annoyance. But for a jet, the air is everything. As you get closer and closer to the speed of sound, the air in front of the jet literally can't get out of the way fast enough. It starts to compress, it gets thick. It almost acts like a fluid. And that creates this unbelievable amount of drag and stress. So what really matters isn't your speed over the ground, it's your speed relative to the air right there with you. This whole phenomenon is what led pilots to talk about hitting an invisible wall in the sky. I mean, can you imagine? They were feeling this massive barrier. And to really understand what was happening, we had to come up with a brand new way to measure it. And here it is, the Mach number. It's named after the physicist Ernst Mach. And the key thing to get is that it's not a fixed speed. It's a ratio. All it does is compare your current speed to the speed of sound in the exact same conditions. And because the speed of sound changes with things like temperature and altitude, Mach 1 isn't the same number on a hot day at sea level as it is up at 40,000 feet, where it's freezing cold. It's a moving target. This quote just nails it. It really gets to the heart of the matter. It's not about miles per hour. It's about your relationship with the sound waves all around you. Are you slower than them? Are you faster? Or are you right on the edge, pushing them along? That one single idea is what the Mach number tells us. And here we have it, the magic number, Mach 1. This is that precise moment when you're traveling at the exact speed of sound. Crossing this line is what we call breaking the sound barrier. It's the point where an aircraft goes from pushing a wave of pressure in front of it to completely outrunning it, which is what creates that incredible sonic boom. But here's the thing, breaking Mach 1 is really just the first step. Once you're past that, this whole new world of flight opens up. I like to think of it as a speed ladder. Every rung you climb up represents a totally different and way more extreme way of interacting with the atmosphere. So here's the map for our journey up that ladder. We start down at subsonic. That's where pretty much all commercial flights live. Then you punch through to supersonic, you climb up to hypersonic, and then you reach speeds that are just almost hard to even wrap your head around. Each of these regimes presents its own brutal engineering challenges. And you can see that first big shift right here. During subsonic flight, the air just parts smoothly, kind of like a boat gliding through calm water. It's predictable. But when you go supersonic, the air has zero time to react. The aircraft is literally slamming into it, creating these powerful shock waves, these cones of compressed air that trail behind it and create the sonic boom we hear on the ground. Now, to put this into perspective, your average passenger jet is cruising at about Mach 0.8, so it's comfortably under that sound barrier. The amazing Concorde, it flew at Mach 2, twice the speed of sound, and a modern fighter like an F-15 can push beyond Mach 2.5. The jump in energy and the kind of engineering you need to go from subsonic to supersonic is just immense. We're talking completely different engine designs, different materials. Everything has to be stronger. But going from, say, Mach 2 to Mach 5, well, that's another leap entirely. This is when we enter the realm of hypersonic flight. And up here, at more than 5 times the speed of sound, the physics just gets completely wild. The rulebook gets thrown out the window. Okay, welcome to the very top of the ladder. We're now talking about speeds that are so incredibly high that the air itself starts to break down under the stress. These are challenges that honestly sound like they're straight out of science fiction. So at high hypersonic speeds, we're talking above Mach 10. The friction generates so much heat, it can literally rip air molecules apart. It changes the chemistry of the air. Then you get above Mach 25. These are the re-entry speeds for spacecraft coming back to Earth. At this point, the vehicle isn't flying through air anymore. It's surrounded by a superheated layer of plasma. That's the same state of matter you see in stars. It's just mind-boggling. So what is it actually like for a shuttle coming home? It's basically a controlled fall through fire. It's insane. First, the atmosphere hits it like a giant brake, creating crushing G-forces. Next, the vehicle gets wrapped in this glowing sheath of plasma that's hotter than the surface of the sun. And somehow, through all of that, it has to navigate with pinpoint precision to land safely on a runway. It's truly one of the greatest engineering feats in human history. So, why? Why does any of this matter? Why are we pushing the boundaries to these unbelievable speeds? Well, it's not just about setting records. It's really about building our future. Mastering hypersonic flight could mean traveling from New York to London in under an hour. It unlocks faster, cheaper, and more efficient access to space. And all the materials and the technologies that we have to invent to withstand these extreme conditions, they end up in everything from medicine to the phone in your pocket. Understanding the Mach scale is like looking at the blueprint for the next generation of human exploration. So that kind of leaves us with this one big question. Less than 100 years ago, we broke the sound barrier. Today, we're literally navigating through plasma. As our technology just keeps accelerating faster and faster, what do you think humanity's next sound barrier will be? What's the next great wall we have to break through?